So, Samuel, you mentioned MDPs. They're the engines, right?
Exactly. MDPs define the rules of the game for reinforcement learning agents.
Okay. And what's the problem with simple plans in these environments?
Well, simple plans don't adapt. MDPs are dynamic. The world changes. A plan made in one state might be useless in another.
So, these algorithms cheat by having full access to the MDP?
Yeah, they know everything about the environment. This isn't always possible in real-world scenarios.
So, value iteration and policy iteration are these cheat methods?
They are fundamental methods for solving MDPs using dynamic programming, which is a really powerful technique.
But they rely on knowing the environment deeply?
Exactly. You need to know the transitions and the rewards. They tell you exactly what will happen.
Why is that a problem?
In real life, you often don't know all the details. Environments are complex and can change unexpectedly.
So, why are these methods valuable even if they're simplified?
They're foundational, man. They show us how to think about reinforcement learning. Almost all other RL algorithms build from these concepts.
So, what happens when you know everything and don't need to explore?
No uncertainty, no need for exploration. You directly calculate the best path. It's like having a map and following the optimal route.
And that's supervised learning?
Well, you're given the perfect answer. You're not testing the agent's reactions.
So, you're isolating sequential feedback?
Right. Separating that from the messy trial and error of real reinforcement learning. This chapter is looking at clean, simplified learning.
That's helpful for understanding, but how does that fit into real-world learning in DRL?
It's a crucial stepping stone, showing how algorithms operate in ideal conditions. Then we can move on to the more realistic situations.
So, Samuel, the goal of a decision-making agent is maximizing rewards. But how exactly does this work?
Yeah, it's about finding the best sequence of actions. Think of it like a long game, where you get points for doing things right.
Rewards, how are they measured?
They're like little points you earn at each step. It adds up the points over time. And there's this idea of discounting.
Discounting?
Imagine a reward now is worth more than a reward later. You might get a small reward now, but a big one in the future.
Makes sense. You mentioned a slippery walk 5 example?
Right, it's a simple environment, like a grid, but with some randomness. If you move right, sometimes you slip and go left.
So, unpredictable, huh?
Precisely. That makes it more interesting, more like real life.
And how do you calculate the return?
You add up all the rewards you get, along the whole path to the end goal. That's the total return.
So the sum of all rewards?
Exactly. And we can adjust that sum based on how much we value rewards earlier in the process. That's the discount factor, gamma.
So, you basically prioritize early rewards over later ones?
That's right. The future rewards get less and less important.
So, if you get a reward early, that's weighted more than one you get later?
Correct, but the importance of the reward depends on how much you discount future rewards.
Okay, let's say an agent in this slippery walk 5 goes 3, 0 for 0, 5, 0 for 0, 5, 0, 6, 1. What's the return?
Well, without knowing the discount factor, we can't be precise. It depends on how important future rewards are.
A crucial concept you explained is the reward to go. Can you elaborate on what that means?
It's like, what's the best reward you can get from here onwards? Thinking ahead, essentially.
So, the agent considers the potential rewards as it proceeds towards the goal?
Exactly. It's a forward-looking way of looking at things.
This is all very interesting. So how do you apply this in real-world scenarios?
Well, think about self-driving cars, for instance. The reward might be avoiding accidents or optimizing routes.
Okay, Samuel, so we're talking about optimal policies in reinforcement learning. You mentioned the frozen lake example. Can you explain this a bit more?
Sure. It's a simple environment. You know, imagine a grid. Some squares are safe, some are holes, and one is the goal. The agent's job is to get to the goal.
So, the agent just has to go right?
Well, it's not always that simple. The environment is stochastic, meaning its actions aren't predictable. Sometimes, even if you try to go right, you might end up going left.
Oh, so it's random? Like a dice roll?
Exactly. The agent needs a plan, a policy to cope with the unpredictability. It has to consider, not just what might happen, but the likelihood that it happens.
So, how does this policy work?
A policy tells the agent what action to take in a given situation. It's a kind of rulebook. It tells the agent, if you're here, do this.
And can policies be different from each other?
Definitely. There can be multiple policies, even multiple optimal policies for a given environment. Think of different strategies for navigating the same maze.
Okay, so what's a value function? Is it like the worth of a policy?
Kind of. It estimates the return the agent can expect from a given state. It helps the agent figure out which moves are more valuable in the long run.
So, in this frozen lake, if you know the best way to go in each spot, what does the best policy look like?
Well, it's pretty clear, right? Go right as much as possible. But this always go right idea isn't good enough for every situation.
Right? Because the environment is not entirely predictable.
Exactly. The agent needs to account for the possible random movements, and that's what value functions help with. They calculate the expected return from each state and action, giving a better picture of the optimal path.
So, the agent isn't just choosing actions. It's anticipating what might happen next, learning from the uncertainty.
Precisely. It's about maximizing the expected return, considering the probabilistic nature of the environment. And unlike the simple always go right, it tells how valuable any possible action is for each state. That's why policies aren't enough. We need to estimate returns.
So, Samuel, you're talking about action value functions. Can you break this down for us? Like, what exactly is an action value function?
Sure, Alfred. Think of it as a way to figure out how good an action is in a given situation. It's not just about the state itself, but about the action you take within that state.
Okay, so it's about the action in the state. That makes sense. But how does that help us choose better actions?
Well, imagine you're at a crossroads. You could go left or right. The value of the state itself doesn't tell you which way is better. But an action value function, or Q function, tells you the expected outcome if you go left or right.
So, it predicts the future reward?
Exactly. It gives you the expected return if you choose a particular action and then follow a specific policy afterward.
And what's a policy?
A policy is a strategy. It tells you what action to take in each state. So a policy could say, always go right, for example.
Gotcha. So, the Q function tells us the expected value of taking an action under a policy. How is this different from just looking at the value of a state?
It's crucial. A state's value doesn't consider the action. The Q function considers the action, the policy, and importantly, the expected rewards.
You're saying the Q function considers how an action changes the environment?
Yes. A state value, let's call it the V function, doesn't reflect the environmental dynamics like the Q function does. It just shows the overall worth of a position. The Q function is crucial for improving policies, especially in complex situations.
Right. How do we calculate this Q function?
Well, there's a recursive equation, the Bellman equation. It essentially estimates the value of an action by considering the immediate reward and the value of the next state. We need to weigh the probabilities of those next states and rewards to compute the value.
So, it's weighing immediate rewards and then future rewards too? That sounds complex.
It is, but it's a way to look at an action's long-term effect, not just the immediate one.
So, in simple terms, how do we use the Q function in a reinforcement learning problem?
By comparing the Q values of different actions. The higher the Q value, the better the action is expected to be in a given state. This lets us adjust the policy to maximize rewards over time.
That's really helpful. Thanks, Samuel. So, Samuel, you're saying this action advantage function, it's basically a measure of how good an action is compared to the usual policy, right?
Exactly. It tells you how much better an action is compared to just following the existing plan.
Okay, so it's a difference, a comparison? Can you give me a real-world example?
Sure. Imagine you're playing a game. Your policy says always go left. But sometimes going right might be better. The advantage function pinpoints just how much better that right turn is, compared to the default left turn.
So, it's like a risk-reward thing?
Precisely. It quantifies the extra reward or penalty from deviating from your policy.
And this helps a reinforcement learning agent?
Absolutely. It lets the agent figure out which actions, though outside the usual policy, are actually more worthwhile. It's about exploring beyond the known path.
How does it relate to the Q function then?
The Q function gives the value of taking an action in a state given you're following a policy, after taking the action. The action advantage function takes into account the value of the state itself under the same policy. It's a way to measure the actual effect compared to just the expected effect.
So, it's not just about the action's value, but also about how the action impacts the overall state, right?
Exactly. It's the difference in reward between choosing a specific action and sticking with the initial policy.
Interesting. So, if the advantage is negative, it suggests
that sticking with the policy is better than taking the specific action.
Makes sense. And how do we get this advantage function? Do we calculate it in some way from existing data?
Yes, you calculate it from the Q function and state value function. The policy dictates which action to take.
So, this action advantage function is crucial for smarter decision making in reinforcement learning?
Yes, it allows agents to evaluate actions more effectively and explore their potential beyond the current policy's limitations. It's about efficiently finding better alternatives, which is really key to learning and progress.
Okay, Samuel, so optimality. What exactly does that mean in the context of reinforcement learning?
Optimality, in RL, is finding the absolute best possible behavior. It's like the gold standard.
So, a best performing policy?
Exactly. A policy that, given a state, consistently leads to the highest expected rewards.
And these state value functions, how do they fit in?
They represent the expected return from being in a particular state. The optimal one maximizes those returns, no matter which policy you use.
Makes sense. But what's the difference between an optimal policy and the optimal state value function?
The optimal policy tells you what action to take. The optimal state value function tells you how good that state is, in terms of the value you can get.
So, the optimal state value function is just the maximum value for every state, no matter the specific policy?
Exactly. It's a single, consistent maximum value, independent of the policy.
Interesting. You mentioned optimal action value functions too. What's the deal with those?
They measure the value of taking a specific action in a particular state. The optimal one, again, is the maximum value for every state action pair.
So, it's kind of like a more specific version of the state value function?
Yes, you can get the optimal state value function from the optimal action value function. It's all connected.
And the action advantage function?
The action advantage function tells us how good an action is relative to the optimal state value function. Crucially, it's always less than or equal to 0 for optimal actions. If it's better than 0, there's a better action possible in the same state.
That's a fascinating way of looking at it. So, you can get the optimal policy if you have the optimal Q function?
Precisely. You don't need the full MDP environment if you have that. You can calculate the optimal policy directly from the optimal Q function.
Wait, if you have the optimal V function, you can get the optimal Q function?
You can do a one-step search.
So if you have Q, you get V. If you have V, you can get Q, and then you find your best policy. It's a really powerful idea.
Absolutely. It simplifies a lot of the calculations.
So, even though there might be multiple optimal policies, there's only one optimal V, Q, and advantage function?
That's right. It's a single best measure in each case.
This is really helpful. Thanks, Samuel. So, Samuel, we're talking about evaluating policies, right? This iterative policy evaluation. What's the core idea?
Yeah, it's about figuring out how good a particular policy is. Basically, we estimate the value of each state under that policy.
Okay, but why estimate? Why not just calculate it?
Well, sometimes the state space is huge. Calculating the value for every state directly is impossible.
So, this iterative method gets around that problem. How does it work?
Exactly. We start with a guess for each state's value. Then, we update those guesses based on the policy and expected rewards.
And how do we update those guesses? What's the magic formula?
It's an equation, iteratively improving the estimates. You calculate the value of a state by considering the reward you'll get and the discounted value of the next state.
Discounted value? Why discounted? That's interesting.
Because future rewards are worth less than immediate rewards. Think of it like saving for retirement. $1 now is worth more than a $20 years from now.
So, you're giving a lower value to future rewards?
Right. The discount factor, gamma, is a number between 0 and 1. A lower discount factor means rewards in the distant future become almost insignificant.
Makes sense. So, this process continues until the values stop changing much. We hit convergence.
Exactly. Or until we reach a preset tolerance. We don't need perfect accuracy.
So, you're saying we're not aiming for perfect accuracy. We just want an approximation?
Exactly. An accurate enough approximation for our purposes. This method is guaranteed to converge, eventually.
What about real-world applications? Where might we use this?
Lots of places. Think robotics. We could evaluate policies for a robot navigating a maze. Or even optimizing supply chains.
So, essentially, we're trying to find the best path, the optimal policy.
Precisely. By iteratively improving our estimates, we approach the best possible outcome for the current policy.
Good point, Samuel. This iterative policy evaluation, it's a smart approach. Thanks. So, Samuel, this policy evaluation seems pretty fast. 8 iterations to get a good estimate?
Yeah, pretty impressive. It's all about the environment. Discrete states and actions really help. You know, think of it like a simplified game. Fewer options mean quicker calculations.
But wait, what exactly is a state value function?
It's basically how good a state is for a given policy. Imagine, in a game, every possible position on the board. The state value function gives you a score for each of those positions, based on how likely that position leads to a good outcome.
So, a higher score is better?
Exactly. The higher the value, the more likely that state leads to a high reward in the long run. And this randomly generated policy, performing quite well after just 8 iterations? That's a surprising result.
So, the randomly generated policy is performing surprisingly well?
Yeah, the values improve with each iteration. The calculation keeps fine-tuning the estimate.
And these values, like 0.09 SS and 0.1469, what do they represent?
Those are the estimated values for different states. Higher values mean the policy is more promising in those specific states. You know, it's not a perfect value, but it's highly accurate, especially given a gamma of 0.99.
0.99? What does that represent?
That's the discount factor. It weighs future rewards less heavily than immediate rewards. A higher gamma means future rewards matter more.
Okay, I'm getting the picture. So, these values, like 0.4957, are telling us how much reward that specific state will bring?
Yes, they are estimates. The value function reflects expected long-term rewards based on the policy.
Interesting. And you mentioned earlier different policies. What about the go-get-it policy?
The go-get-it policy didn't do so well, surprisingly. It only reached the goal state a small percentage of the time. There are many factors impacting this. The environment and its rewards are critical.
So, it's all about the specifics of the environment?
Precisely. A policy performs well in certain environments, but might not generalize. The results highlight the importance of environment modeling.
Fascinating. So, there's a trade-off between speed and accuracy. Is that always true?
Not always. Well, the trade-off is dependent on different factors. It truly depends on the task. In many cases, faster solutions are good enough for use cases.
A great way to frame that. Thanks, Samuel. Okay, Samuel, so we're talking about optimal policies in reinforcement learning. You mentioned multiple optimal policies are possible. Can you unpack that a bit?
Yeah, absolutely. Sometimes, there isn't just one single best way to act. Think of driving to work. There might be multiple routes that are equally fast and efficient.
So, the environment has options?
Exactly. The FL environment, in this case, has multiple paths to success. The algorithm figures this out, finds different paths that lead to optimal rewards.
Interesting. And what about this specific example with state 6?
In state 6, The algorithm found two actions, left or right, are equally valuable.
So, no single best move?
Right. The action value function shows a tie. This is significant because if the algorithm randomly chose one of those actions, it could potentially keep cycling between different policies, not improving upon the existing ones. It's a practical consideration.
So, what's the solution?
We need to make sure tiebreakers are handled carefully. You can't just randomly choose. The algorithm needs a consistent method to avoid getting stuck in cycles.
Gotcha. That's a clever way to ensure efficiency.
It's important to understand the implications of ties in the action value function. These ties represent points of minimal improvement, where small steps in a particular direction don't lead to discernible gains. Sometimes these are unavoidable, and you need to account for them to get a stable optimal policy.
Policy iteration. You said it's guaranteed to find the optimal policy. Why is that?
The mathematical proof behind policy iteration shows it won't get trapped in local optima. It systematically improves the policy and guarantees finding the globally optimal path.
That's comforting. What other algorithms exist for finding these optimal state value functions and policies?
There are many, but policy iteration is a strong one, because it directly iterates on the policies, guaranteeing convergence to a global optimum. Other methods exist, such as value iteration. They have different trade-offs.
Fascinating. This is a critical concept for optimizing in deep reinforcement learning. Thanks, Samuel.